In this video, I'm going to talk about how to develop control charts, specifically X bar and R chart. So the whole idea of control chart is actually very simple, but it's very novel. Okay, so you are essentially constructing three lines, beginning from what's in the middle. This is your center line. This represents your process mean. And you also will establish two more limits. One is upper control limit. It's not specification limit. Don't get confused with the spec limit. And you also establish lower control limit. Okay, so what you do with this is your control limits. One is upper and lower. They're usually 3 standard deviations away from the center limit. Okay, the idea is for each sample you are drawing from your production line or service delivery processes, you plot the sample average continuously. So as you can see, for example, this is your first hour sample result. This is your second hour sample result, third hour sample result, fourth hour, and so forth. As you continuously plot your sample averages, if you have detected that sample average has went beyond the upper control limit or below the lower control limit, that may be an indication that your process mean has shifted. Okay, for those of you who participated in previous class, you may remember that I discussed the implication of process mean shift. Sometimes it will go undetected. Okay, a machine can change its process mean as long as you can detect it early. It won't bring too much economic damage, but if it has gone undetected, it will most certainly give you piles of unacceptable outcomes. Okay, so therefore the control chart is actually a mechanism you use to detect changes in any of the two process characteristics, specifically shift in mean or changes in your variability. So you'll be seeing that we're going to discuss two different forms of control chart. One is we're going to talk about, first one is how to develop the X bar chart. X bar chart is specifically being used to detect the shift in mean. And the second chart here is R chart. This chart is being used to detect the changes in the process standard deviation. Okay, so the whole idea is, first you need some historical data to develop your upper control limit, center line, and lower control limit. And in each one of the sample result that's coming out from your production line or service delivery processes, you would put it on your control chart to see whether that has go above or below your control limits. If it did, that means that's an indication that your process may have shifted its mean or changed its standard deviation. Okay, so therefore you can take some corrective action. So in nature, the control chart is nothing but a detection mechanism. Again, just let me emphasize a little bit more, just in case you didn't understand in my previous explanation. So your upper control limit, center line, and lower control limit, this is essentially usually center line is your process mean or expected process mean, and upper control limit is 3 standard deviation above the center line. Lower control limit is 3 standard deviation below the center line. So we still use that empirical rule to kind of detect the shift in mean, because whatever go above that 3 standard deviation bound, it's deemed suspicious. Therefore, you have incentive to stop your line to kind of conduct some inspection. Okay, so why it's suspicious? If it has gone beyond the upper control limit or below the lower control limit, that's because according to the empirical rules that we discuss a lot, everything stays within 3 standard deviation range. Almost everything will stay within that 3 standard deviation range. Okay, 3 standard deviation before the average and after the average. If something has gone outside of that bound, maybe it is extremely rare case, but also it could be that your process mean has shifted. Therefore, you start to produce something from a very different process mean. Okay, that is the reason why when you see something went beyond the control limit, we usually conduct a full stop, and we usually do a full stop of your machine or service processes and conduct a thorough evaluation. Maybe that's a false flag, but it's still, if something went beyond or below the control limits, that kind of warrants some kind of inspection or investigation. Let's take a look at an actual problem. So 12 samples, each contains 5 parts. This usually means that you have to draw 12 different set of samples, and each set, your sample size is 5. Okay, so there are 12 groups of samples, and each sample group has 5 parts. That's what it says. Essentially, your sample size is 5, but you have to repeatedly draw this for 12 times. In total, you have 60. You have 12 groups, and each group, your sample size is consistent in 5. Okay, we're taken from a process that produces steel rods in Emmanuel Cotzi factory. The length of each rod in the sample was determined. The results were tabulated, and sample means and ranges were computed. The results were. So you look at the first column, this is sample ID, and the second column is sample mean. Okay, and the range is this. Range is defined as a difference between the biggest in the group, a difference between the biggest in the group and the smallest in the group. Okay, because this is talking about what? Some kind of rod length. Therefore, the range is basically the difference between the longest rod in the sample group minus the shortest rod in the sample group. That's basically the differences between the maximum and the minimum. Okay, it has already been calculated for you, so you don't have to, actually do this. So the sample mean is 11.704. Okay, so at this point we don't really know what is the sample, what is the process mean, but what we can do is we can actually infer the sample mean by summarizing the sample data like this. So I'm gonna do it as usual, copy and paste it. I'm gonna move it beneath here so that's easier to work with. Okay, and those I can get rid of it. So first I want to develop X-bar chart. X-bar chart requires center line, and it requires upper control limit and the lower control limit. Okay, so you kind of have to borrow the equation from your lecture notes, but I will tell you how to do that. So your sample size in this case, it's another very important thing. You need to determine what is a sample size. You're not going to need sample size for calculation. You just need to know what sample size is. Okay, so sample size is 5. And for X bar chart, you need to find out the center line. Center line is usually your X bar bar. It's your X bar, and if you look at your lecture notes, X bar is what it is. Your upper control limit is defined by the center line, which is X bar, plus a constant A2 multiplied by the R bar. So earlier I said a 3 standard deviation. Okay, 3 standard deviation. So that's when your standard deviation is a known information. In a lot of cases, that information is not known to us because, this is important, because the sample size is extremely small. So usually, in order to measure standard deviation reliably, you need to have sample size that's fairly big, fairly large, and 30 and above. Okay, so if your sample size is so small, it's less than 12, 11, 10, in this particular case, sample size is only 5, we cannot get a very reliable standard deviation measure. That is just homework for statisticians, okay? And their solution is, hey, work with a range. Work with a range. Range sometimes can be a very good approximation of standard deviation, and A2 and R bar is basically something that they have created so that we don't have to work with a standard deviation, but just work with a range, something that's much easier to calculate, therefore to substitute the missing information here, which is a standard deviation, okay? So I mean, if you're not interested in all these things, just remember when sample size is small, and what you need to do is you need to get X bar, and you need to pick correct A2 number from the table that I'll be providing soon, and then you multiply that with your R bar. What is R bar? R bar is basically average of all ranges. So you need something here, R bar. So X bar is average of all the averages here. So basically those are the sample averages. So when you measure the length of 5 rods, and you can usually get a sample mean whenever you measure 5 different rods in terms of their length. So you are averaging all those averages, okay? Therefore, this something a lot of times can become very reliable estimation for your process center, okay? So therefore, center line is established. And your R bar is average of all the ranges. So in this way, we got R bar. Since X bar and R bar are calculated, and next thing you want to do is to look up the A2 value so that you can complete your UCL, LCL. Let's see that, okay? So your A2 value. What is your A2 value? Where do you get that? So usually this will be provided. Oops, let me do it again. This table right here. This is somewhat like your number tables, and a lot of times you can find it in the internet, or a lot of times if it's an exam, those constants will usually be provided. Okay, the quality professionals, they usually have a little bit of handbook that has all those informations contained. So this is a sigma, right? 3 sigma distances, and our sample size is 5. When sample size is 5, the A2, the corresponding A2 in this particular case, as we looked it up, it's 0.577. Okay, so and then your UCL is of course your center line plus A2 multiplied by your R bar. Okay, and your lower control limit is your center line minus A2 multiplied by your R bar. This is essentially the quantity we just added or subtracted, which is A2 multiplication R bar. This particular quantity is essentially the same or approximately the same with a 3 standard deviation that we talk a lot. We can't do 3 standard deviation 3 times standard deviation, because standard deviation is something that is not known to us. We only know range. Okay, we don't have standard deviation because our sample size is too small. So we're done with X bar chart, and next step is we want to develop our R bar chart. Remember, R bar chart is used to detect change in process standard deviation. Okay, so in this case, you need to have what? You need to have D4 times R bar, D3 times R bar. So you need to have a D4 factor, you need to have a D3 factor, and you need to have R bar, which we already calculated up there. And then you can develop your upper control limit and lower control limit for your range. So your D4 in this particular case, for the sample size of 5, is 2.115, and then D3 is 0. D3 is 0, and your R bar again is this, and your upper control limit is basically D4 times R bar. Your lower control limit will be 0 times R bar. Okay, so this has given you a upper control limit and lower control limit. So whatever sample that's coming next, so for example, if there is a next sample, if there is a next group of sample, which is sample 13, with a sample in 11.718, and the range has returned as 0.056. So you compare that against upper control limit. You can compare against the sample size here first. So I'm sorry, sample mean first. Sample mean is within this particular range. That means sample mean has not changed. I'm sorry, the process mean has not changed. I'm sorry, so sorry. So let me say it again. So if you compare that sample average against the control limit, If this is within this particular limit, that means your process average or process mean has not shifted, at least according to the sample result. And then you compare this against this particular range. It's within this particular range. That means your process standard deviation or standard variability has not changed. Okay, but if you got like another sample that says Ch06s, okay, or maybe like this, that means this means what? This means your sample average is outside of this bound. That means what? Your process mean is very likely has changed. Therefore, what you need to do is you stop the machine and conduct a full inspection just to make sure. If it's broken, fix it, and then you can restart your production. Okay, so in some cases, your process mean has become normal like this. Okay, however, your range may have changed. So did it? Okay, it looks like yeah, I should do this. Okay, and did R bar? Yeah, R bar didn't change. X bar. Okay, this is normal. So this is outside of the bound. I mean to make it within the bound. So process mean has not changed, but in some cases your range can say this. And this range is atypical compared to the rest of the ranges. It's also outside of the control limit. You can say that you can say that, oh, let's stop the machine. Maybe the process standard deviation has changed. What is the consequences of changing process standard deviation? Especially it has gotten bigger. Because getting smaller, we're not going to worry too much. It is when getting bigger that kind of worries us. You're going to start to output a lot of uneven outcomes that may increase your DPMO. Okay, this is everything about control charts that I want to discuss in this particular chapter. So essentially, your takeaway is that when the sample size is very small, you need to learn how to work with this particular number table, okay, using the A2 and D4, D3 to develop corresponding upper control limit for each of the X bar chart and R bar chart. You also need to know what is the purpose of using our X bar chart, what is the purpose of using R bar chart, what is being detected, what is being inspected, why things are being inspected, and things like that. Okay.